everyone, I wanted to go through and just quickly explain how to find eigenvalues and eigenvectors with Maple, just so you had some computer algebra system that you knew how to do this with. So remember, when we're doing linear algebra in Maple, we always start with linear algebra semicolon. We have to start there. And if we do a semicolon, what comes after are all the commands we can use. So notice right here we can get eigenvalues and eigenvectors. So I'm just going to enter this matrix here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my matrix, and it appears. I always end my command lines with semicolons or colons. And then if I just wanted to get the eigenvalues, then, oh, hold on just a second. There we go. If I just wanted to get the eigenvalues, I can just type eigenvalues of M, and there they are. There are 3 eigenvalues. The first one is 0, which means that this is a singular matrix. And then here are my other 2, which are irrational numbers. What I really want, though, are not just the eigenvalues, but also the eigenvectors. So I type in eigenvectors of M, and out comes this long list. And so I wanted to talk to you about what this list means. Okay, so if I look at the end of the list, it might make a little bit more sense. What you're going to notice is that in each list, and we have a list of lists, or really a list of arrays, the beginning of each of them we have one of the eigenvalues. Okay, and so that's trying to tell you the eigenvectors that go with each eigenvalue. Now, the next number next to the eigenvalue, that 1, that is the multiplicity of the eigenvalue. So if you think about the characteristic polynomial as a polynomial, and the eigenvalues are the roots of the polynomial, the multiplicity means the same thing, or the algebraic multiplicity means the same thing that it does in regular algebra. It's the number of times that eigenvalue is a root, or in other words, it's the degree of, say, lambda, or lambda minus that eigenvalue, or lambda minus that eigenvalue. Okay, it's not anything you need to worry about right now. And then that part that's in the brackets, that is the eigenvector. It's just written as a row vector, and there are no commas. So for the eigenvalue 0, the eigenvector is 1, -2, 1. For the eigenvector 15 halves minus 3 halves comes the square root of 33, the eigenvector is this -1/2 minus 3 over 22 times the square root of 33. That's the first entry. The next entry is 1/4 minus 3/44 times the square root of 33. And the last entry is 1. There's actually a space between each of those numbers. It's a little bit hard to see. So that's what that means. If you want instead for the numbers that you see to not be irrational, and you want a decimal point approximation instead, you're going to do the same commands, but you can put them inside eval f. That's going to be a floating point decimal approximation. So let's go ahead and find the eigenvalues just like we did before. Only we're going to put a val f around it, and you see that our eigenvalues are 0, and then these 2 decimal approximations of the irrational numbers that we had before. And if we have an integer, notice that 0 is followed by a decimal point because it's trying to approximate it, even though 0 is the exact eigenvalue. We can do the same thing for the eigenvectors. And if we do that, our eigenvectors become a little bit more clear. Notice that, well, this one's in a different order than it was before, but here I have the eigenvalue of 0, it has multiplicity 1, and our eigenvector is 1, negative 2, 1. Remember, that's not the only eigenvector. Our eigenvectors with eigenvalue 0 are any non-zero multiple of 1, negative 2, 1. Then our eigenvalue, I keep moving that screen around, oops. Our eigenvalue of 16.11684397 has multiplicity 1, and here are the 3 components of one eigenvector. And likewise for our third eigenvalue. All right, let me know if you have trouble with the computer algebra system finding the eigenvalues or eigenvectors. And I will see you in class tomorrow.